Okay, the first thing that I do when I have a nomenclature worksheet is label what type of compound they are. And that helps greatly to label what type of compound they are. So I'm going to take the first 10 of these right now, and we're going to label what type of compound these are. So HCl-AQ. Immediately when you see that AQ, what does that tell you? Acid. You have an acid. And then what you look at is, do I have two different elements here, or do I have more than two? I only have two. So what kind of acid is it? Say it. Binary acid. It's a binary acid. So I'll put Ba. I'll put Ba. Now, I did not, who has their nomenclature notes? Can I see your nomenclature notes, Lucas, please? Anybody have the nomenclature notes? Do you have anything you can have on there? Actually, let me have it. Is that acids? Guys, if you all printed out nomenclature, you printed this page out. This is a good page to kind of review every so often because it does help us label the different compounds. And you know what I'm seeing? It doesn't have what I wanted it to have. It doesn't have acids on it. Does the other page have acids? Does the second page have acids? I didn't think it did either. Okay, well then I do need the acid page. Can I borrow the acid page? Okay. This is good for everything but acids. And what this really is very much, it's a longer format, but it's very much what was in your notes a couple of days ago's notes, where I had the compounds and then I showed you the different types of compounds, ionic and molecular, and right before we talked about, I think you all had it in your notes. Am I right? Did you have that in your notes? I threw away my notes, so I don't know. I think it was. If it wasn't, then you have this page. So ionic compound, pay attention to what this tells you, molecular compound, etc. Now, what I really wanted to do, and you guys have all watched the videos on this, I'm assuming. If you haven't, then that's totally bad, honestly, because you're way behind if you haven't watched these videos. But here's an acid page. So when you get anything with AQ, as soon as you see AQ, you know you have an acid. And then your two choices are binary acids and tertiary acids. So what you're looking for in a binary acid is two different atoms, which is going to be hydrogen and a nonmetal. What you're looking for in tertiary is hydrogen and a polyatomic ion. As soon as you know you have an acid, then your next thought is, and how you're going to know you have an acid, if it says AQ or acid, period. AQ or acid, you know you have an acid. If you have two different elements, so in other words, you have hydrogen and a nonmetal, then it's a binary acid and it will say hydro something. If it has three different elements, three or more different elements, then it's a tertiary acid and it will not say hydro. So those are the two different things you're kind of looking for. Hydrogen is in all acids though, so you balance the charges just like you would normally with hydrogen in all acids. Okay, so make sure that you kind of practice through these. So I'm going to put this back together for you. All right, so we know that this is a binary acid. All right, go to the next one. As soon as you see PB, what are you looking for? Lead. And then you say, okay, that's a, what kind of element? It's a metal, then where is it? It's a transition metal. So it's a transition ionic. Then you see magnesium, and you say, what kind of element is that? What kind of element is magnesium? It's a metal, so is this an ionic compound? Now, some of you are looking at me and you're really looking like you have no idea what I'm talking about. And if that's the case, then that tells me you haven't watched the videos. let me show you something. This, I don't have my normal well, I do have my normal periodic table. It doesn't matter. This is a periodic table just as well. You have, can I write on this? I guess I can after I'm already writing on it. Do you see that stair step? Anything to the left of that stair step is going to be a metal. Anything to the right side of that stair step is a non-metal. That's how we know if it's a metal or a non-metal. So if it's to the left of the stair step, it's a metal. If it's to the right of the stair step, it's a non-metal. So when I look at magnesium, it's a metal. It's not a transition metal because a transition metal is anything in this space. Anything between my hands is a transition metal for purposes of charges. Anything there is a transition metal. These all have a fixed charge, +1. These all have a fixed charge of +2. We know aluminum is always +3, the column is +2, and the silver is +1. But everybody else in this area could have a varying charge. Have we just talked about that with what we did last week? Did we talk about that? Then here, let's see if you know what I'm talking about. What is a logical charge for iron? Say it. It's a logical charge. +2. +2. Why is it +2? How does iron become +2? Somebody over here tell me, why does iron become +2? How does it become +2? The logical immediate is it what? No, we're not talking about making compounds. How does it become +2? It loses 2 electrons. That's immediately the logical. It loses 2 electrons. Then my question is, where does it lose 2 electrons from? Tell me, Josh, exactly where?
The alkali metals and alkali earth.
So what energy? Tell me energy level and subshell. Energy level is? Nope. 4. And what subshell is this? S. It loses 2 electrons from the 4th energy level S subshell. Yes or no? Okay. Now, how many are in D? 1, 2, 3, 4, 5, 6 are in D. Stable is full. Stable is completely full. It's nowhere near completely full. Stable can also be exactly half full. We know, if we've studied our ions, that iron has 2 charges. It has a +2 charge, which we just verified, easy. But it also has what? A +3 charge, which is also a logical charge, because if iron loses 1 electron out of 3D, does it now have an exactly half full subshell? And that's stable. That's more stable than when it's got 6 in it. And so how does iron become iron +3? Iron loses 2 electrons out of the 4th energy level S subshell, and it loses 1 electron out of the 3rd energy level D subshell. Those are questions that could be on your test, guys. What I'm talking to you about right now. But it also helps you with nomenclature, because it's also confirming, oh, these can have more than 1 charge. And these are the reasons why they have more than 1 charge. Okay? Now, all of these are not logical. The ones that I've given you are not all logical. Silver is always +1, and that's totally illogical for most of us. But there are also exceptions I'm not teaching in this class. Okay? But a lot of these that I've asked you to learn, like tin-2, tin-4, lead-2, lead-4, very logical charge, based on what electron configuration notation tells you. Iron-2, iron-3, very logical charges based on electron configuration notation. Okay? So I've tried to give you some that make sense. All right? Now, going back to this. So what we're looking for is, we're looking for, and I'm going to do this. I feel like I'm repeating myself 15 times if you've watched the videos, but I'm also looking at people that have blank stares, so I'm going to write this down. M equals all nonmetals use prefixes. What does M stand for? What kind of compound? Molecular. I is metal or NH4 or H3O first, balance charges, no prefixes. What's I stand for? Ionic. Who's NH4 and H3O? Ammonium and hydronium. Ti is transition metal. Name needs Roman numeral or old name. BA equals what? What's BA stand for? Binary acid, hydrogen plus nonmetal, say hydro, balance charges. And TA is what? Tertiary acid. Tertiary acid, and that means hydrogen plus polyatomic ion, no hydro, 8 changes to ic, ite changes to us. For those of you that have not practiced nomenclature enough, I would encourage you to write this down on your nomenclature papers and redo them. Do them again. Do the practice again. And that way when you start to label these, you can refer back to that, and that's like your little reminder of what to do. Okay? All right, so let's now go back again. It's hydrogen with a non-metal, and it's got AQ. What does that mean? Binary acid. So it's going to be binary acid. We already did this, so I'm just going back through them again. PB, you only have to look at the first element. PB tells you it's a metal. It's what kind of metal? Transition metal. That's why it's transition ionic. Mg is what? Straight up metal. Is it a transition metal? No, so it's just straight up ionic. H2SO4AQ. Immediately, AQ says acid. Is it a binary or a tertiary? Tertiary, because it has that polyatomic ion. O. Doesn't matter anything else. What's O? Non-metal, right? So it's a molecular. Cu. Ionic, but what kind of ionic is it? It's transition metal ionic. So put Ti. IO3. Now I'm going to point out something here. I will never, y'all got to tell me I'm down, sorry. I will never give you a polyatomic ion just to name. I will never give you a polyatomic ion to name, because I'm not giving you an ion quiz. If I were to give you an ion quiz, it would just be polyatomic ions to name, but I'm not. So is that a polyatomic ion? No. What kind of compound is it? Molecular compound, because it's a non-metal first. So it's a molecular compound. H2Cr2O7, tertiary acid. H3PAQ, binary acid. Ga2, It's ionic, but where is that Ga? Is it transition? Good. So transition ionic. And that's one I haven't given you, but that's okay. You can figure it out. Mg. Mg, what would Mg be? Ionic, regular ionic. Does that make sense? All right, I'm going to stop right there on this labeling. Do you understand what I encourage you to do? It will help you. It will help. Okay? Now, let's go back and name them. Once you do this, you've got half the battle won. So now go back and it's a binary acid. Binary acids say what? Hydrogen. Say hydro, and what does the nonmetal change to? Ic. So the I changes to ic. And so you could put hydro-ic. You could say hydro something ic if you wanted to put that up there. So what do we name it? Hydrochloric acid. Very good. Hydrochloric acid. All right. On our transition metals, what do we have to find out? What charge it is. So we have to look at the nonmetal portion or the anion portion first. What charge? Who is C2O4? Oxalate. What charge does oxalate have? -2. How many oxalates do we have? 2. So what is that total negative? -4. You with me? So 2 times -2 is -4. There's only one lead, so what must that lead's charge be? +4. So the lead must be +4. So the name is lead 4 oxalate, or what else could you call it? Plumbic oxalate. I don't care which name you use. It doesn't matter to me. Yes or no? All right, this one is a straight up ionic. Who is Mg? Magnesium. So the name is simply magnesium sulfide. Now, I haven't mentioned any of this at this point, but let me ask a question. When a formula is given to you, do you need to balance charges? No. Why? Because it's balanced. When a formula is given to you, you know it is a balanced formula. So you don't need to balance charges. H2SO4. Who is this? It's tertiary acid. What do we not say? We do not say hydro. So then the name comes from sulfate changes to ic. Now, if you wrote today sulfic, you have to count it wrong because you don't really know it's sulfuric. But it truly is sulfuric acid. It's truly sulfuric acid. Sulfuric acid. Yes or no? Okay. The next one is a molecular. So do we have nonmetals only? What do we use? Prefixes. Who's the prefix for 7? Hepta. Do we change the ending of the first element? No. So what is it? Hepta. Hepta oxygen. Hepta oxygen. What's for? Tetra. Keep going. Nitride. Hepta oxygen tetranitride. Okay. All right. Cu3. I'll pull that. We can see it all. Cu3. It's a transition ionic. Now, what do we have to do? Do we have to pay attention to the nonmetal part or the anion part because it's a transition metal? How many coppers can there be? There's a copper 1 and a copper 2. We don't know which one it is yet. So we have to look at the anion portion. What is PO3? Phosphite. What charge does phosphite have? -3. We have 3 times something that must equal positive 3. What must that something be? Plus 1. The charge must be plus 1 because plus 1 times 3 is positive 3. So what's the name? Copper 1 phosphite. Very good. Copper 1 phosphite, or what's the other name? Cuprous phosphite. Yes or no? Okay. We only have one of them. How do we say it? Iodine. Do we use mono for the first element if there is only one? No. So we put iodine trioxide. Very good. Iodine trioxide. Very good. Guys, talk to me. Is this helping, hurting? Is it making sense? No, because I'll never give you a polyatomic ion. Never will I just give you straight up a polyatomic ion. Ryan, let me also point out, if by chance I meant for this to be a polyatomic ion, then I would have had to put the -1 charge. And see how there's no -1 charge? Does that make sense? I will never give you a polyatomic ion just to name, though. Never. Okay? So do not call it iodate. All right, the next one is a tertiary acid. We have hydrogen here. We don't say anything about hydrogen, do we? Do we say anything about hydrogen here? No, because it's tertiary. So instead, who is this polyatomic ion? Dichromate becomes who? Dichromic. And it's dichromic acid. Dichromic acid. All right. We also have another acid, but is it a binary or tertiary? It's binary. So what do we say? Hydro. The fact that it's binary, we do say hydro. And phosphorus or phosphide changes to? It's actually phosphoric. If you put phosphic, I would count it correct. But it's hydrophosphoric. Hydrophosphoric acid. Now, the next one is a transition metal ionic. We must figure out what the charge is of this transition element. So we look at our non-metal or anion portion. Who is CrO4? Chromate. What charge does chromate have? -2. You have 2 times something which must equal +2. Each gallium must be what charge? What is it again? +1. Each gallium must be +1. So the name is gallium, Roman numeral 1, who? Chromate. Now, we don't know an old name for gallium. I haven't even taught you anything other than Roman numerals for gallium because that's all you do know. So you just put gallium 1 chromate. You are always, when you're naming, you're always safe to just put the Roman numeral. When I give you an old name, you have to know what the old name means. But I won't give you an old name for gallium because I haven't told you to memorize an old name for gallium. The only ones you'll have old names for are chromic, stannic, stannous, plumbus, plumbic, cuprous, cupric, ferrous, ferric. Those are the only ones. And all those, the S's are less charged than the ick. Not necessarily one, but they're less. All right, last one is straight up ionic. You just name it what the ions are. Who's Mg? Magnesium. And who is ASO4? Arsenate. So magnesium arsenate. Is that helpful? I'm pretty sure I do this on the videos. Don't I do this on the very last video? And don't I even do this? Have I done that on the video yet? I mean, did I do that on the videos? I thought I did. On the last one, I thought I did, but I may be wrong. I haven't seen my video lately, but I thought I did do it. I'm pretty consistent. All right, flip through these if you brought these with you to the names page. And I'm not going to rewrite this, but I have it right there. Okay, so let's label these first 10. What do we label this one as? Say it again. TI, transition ionic. Keep going. Stannous would be what? Guys, the name's telling you. Stannous, what would it be? Transition ionic, yes. Ammonium. What would ammonium be? Say it again. Say it. Ionic. Why? There's two other things besides a metal that will be ionic. What are they? Ammonium and hydronium. Ammonium and hydronium are the only positive polyatomic ions. So ammonium is ionic. Good. Perchloric acid. Do we say hydro? But we know we have an acid, but did I say hydro? No, that means it's from what? A polyatomic ion, which means it's from or we call it a tertiary acid. Potassium permanganate. Doesn't matter what the second part is. What's potassium? Is that a metal? So what kind of compound is this? Ionic, good. Sulfur, what kind of compound is it? Molecular. Lead 2. Transition ionic. Sodium. Does that make sense? Ionic. Mercurous. Transition ionic. Copper 2. Transition ionic. I'm going to keep going for a little bit. Dicarbon. What is it? Molecular. As soon as you see that prefix, that tells you. Plus non-metal, carbon. Calcium. Ionic. And dicarbon's right there again. Molecular. And then the last one I'm going to do is thiocyanic. Acid. Tertiary acid. Good job. Good job. Good job. Okay, I'm going to start backwards. I'm going to start down here at thiocyanic acid. We're going to work our way up. Thiocyanic came from who? Thiocyanate. What is thiocyanate's formula? SCN. What charge does thiocyanate have? -1. So how many hydrogens do I need with it? Only one. And what do we put at the end? AQ. Make a note. If you can't do it like I did, then put SCN -1. And because it's an acid, all acids have hydrogen, and hydrogen's +1. Do you see how I did that? Aqueous, meaning in water. Or aqueous, as some people might say. All right, dicarbon. Make it simple. C2, tetra, 4, F, for who? Fluoride. So C2F4. Now, question on these. Do you reduce in a molecular compound? No, you do not reduce in a molecular compound. You do not reduce in a molecular compound. If it were ionic, yes, but not in a molecular. Calcium, what charge does it have? +2. Hypochlorite. What charge? -1. How many hypochlorites do I need? 2. So I would put parentheses 2. So now I'm doing it here for you so that when you go over here and write it, what's the symbol for calcium? Ca. Do I have a subscript for calcium? No. Hypochlorite, what's the formula? Hypochlorite is what? ClO. ClO. How many hypochlorites do I need? 2. So I put parentheses around the entire hypochlorite. And that's 2 hypochlorites. Question on that? Dicarbon. C2. Hepta. Who? N. So N7. C2N7. Copper 2. What's the charge? +2. Sulfite. What's the charge? Negative what? -2. Copper or sulfite is -2. Cu for copper. What is the formula for sulfite? SO3. Good. You've studied, buddy. Good. SO3. No parentheses. Why no parentheses? Because it's balanced. 1 Cu balances 1 SO3. No parentheses when they're balanced. The only time you would need parentheses is if you needed more than one polyatomic ion. Mercurous. Now this one is a tricky one. Mercurous is the same as mercury 1. They all have a +2 charge, but mercurous symbol is Hg2. So remember that one. It's like mercury 1 is Hg2, mercury 2 is Hg, but it's still +2. What's phosphide's charge? That one's straight off the periodic table. -3. So how many mercurises do we need? 3. How many phosphides do we need? 2. But because mercurous is what? Mercurous is what to begin with? Hg2. What do we have to put? Parentheses and then the 3 and then P2. You have to write it that way. You must put, because mercurous itself is Hg2. That's mercurous, how it spells its name. So you must put Hg2 parentheses 3. Sodium's charge. Sodium's charge. +1. Cyanide. What is it again? -1. Cyanide's -1. So what's sodium's formula? Na. Cyanide's formula? Capital C, capital N. And you need to write these correctly. No little n's, no short little n's. And also, I know you guys, and I'm saying guys specifically, I've seen a lot of you guys who are your manufacturing technology engineering type guys, and you love writing everything in capitals like that. That's wrong. Don't write it that way. Do not write that A that way. That's wrong. Go back to kindergarten and first grade on how we wrote our letters, okay? Lead 2. +2, good. Now on this one, you can actually break it down into 3 things if you don't remember what it is. What's hydrogen's charge? +1. What's phosphate's charge? -3. Really though, hydrogen phosphate is a polyatomic ion. What is the overall charge for the polyatomic ion hydrogen phosphate? -2. Does that make sense? Does it balance? Yeah, so what's the formula? PbHPO4. Very good. Yes or no? Sulfur monoxide. What's sulfur? S. Monoxide. O. Make sense? All right, potassium, what's the charge? +1. What's permanganate's charge? -1. Formula for potassium? K, keep going. Permanganate is what? M, lowercase n, capital O, 4. MnO4. I want to point out something on your homework, and I'm pretty sure I make a comment on this in the notes for the homework somewhere. I may be wrong, but I think I do. You have the opportunity, I will say, because the homework changes depending on which version you get. Everybody doesn't have exactly the same homework. Some of you may come across a nomenclature that's perbromate or bromate or hypobromite or bromite. I haven't taught those to you. But where have I taught you something that's hypo something? Who was that? Chlorate. So it was perchlorate, which was what? ClO4. Chlorate, which is ClO3. Then keep going. Chlorite, ClO2, and hypochlorite was ClO. Now look at the periodic table. Is chlorine and bromine, are they in the same family? So would the bromates do the same thing as the chlorates? Permanganate made me think of that. That's what made me think of it. But it's the same thing. And honestly, you could figure out manganate. If that is permanganate, what would manganate be? MnO3, what would manganite be? MnO2, what would hypomanganite be? Does that make sense? So don't get confused if you get that one on your homework. Now, on your nomenclature in lab, would I give you that? No. On your nomenclature for your test, I wouldn't give you that. But the homework, I don't make I pick which homework problems I want, and when I picked it, I didn't realize one of the choices would have been the bromate thing, but you can do that. It's not, use your brain, it's okay, you can do it. Okay? Perchloric, we just talked about that one. Perchloric does not say it doesn't say hydro, so it's a tertiary acid. Now, obviously, is there hydrogen in an acid? Yes, so we know there's hydrogen over here with a +1 charge. Who is perchloric from? Perchlorate. It came from perchlorate. What's perchlorate? ClO4, what charge? -1. It came from perchlorate, which is ClO4 -1. So do we just need one hydrogen? Yeah, so what's the formula? It's pretty easy. HClO4, keep going, parentheses AQ. Yes or no? Okay. Ammonium, what charge? Silicate. -2. Silicate is -2. Give you a hint on, well, never mind. There's no real hint. Except the fact that silicate and carbonate are both kind of oddballs, and they're both -2. That's kind of how I think of them, but that for most people wouldn't really a hint. But it might be. All right, so how many ammoniums do we need? So NH4 what? Parentheses, good job, 2, and then keep going. SiO3. Stannous, what charge? +2. Cyanate, what charge? -1. Stannous is what symbol? SN. Cyanate is what symbol? OCN, all capitals. How many cyanates do we need? 2, so parentheses 2. Yes? And lead 4 is what charge? plus 4. Come on, don't ever miss one with a Roman numeral, please. That's just crazy. Do not ever miss one with a Roman numeral. It tells you the positive charge. Peroxide's what charge? -2. So lead symbol is what? Pb. What is peroxide? O2. How many peroxides do we need? So, help? Not help? Okay. If you're not really here today, then watch this video later when you get here. Okay? Are there any other questions on nomenclature? Anything else on nomenclature? Did everybody sign in? Okay, so hopefully you realize the importance of practicing nomenclature. And if anybody didn't print those out and wants to have that, pick it up after class. Now, let's move on to trends. So, I think all of us know what trends mean, just to kind of give you an idea, just to kind of get you back in a different range than nomenclature. Hair trends. Hair trends change all the time. In the 80s, for girls, perms were in and big hair was in. I was a teenager in the 80s. It's hard for me to believe now, but, well, it's hard for you to believe possibly. I never had curly hair when I was a kid. I had very straight hair when I was a little girl. And then as I got older, or I started getting perms about the 8th or 9th grade, I started, or maybe not even that, maybe in 7th grade, I got perms. And then I kept getting perms for a while because that was very popular. And so back then in the 80s, it's big hair. Everybody had big hair. And you did your hair every day. You always did your hair. And so now that's not popular. I don't know of any girls who get perms anymore. A long time ago when I was a little girl, when I was born in the 70s, straight hair was in. Straight hair was in. I said girls getting perms. I didn't say boys getting perms. I said girls getting perms. I have heard boys now get perms. Do you get a perm?
It's natural.
It's natural? Okay. I have heard, though, that boys get perms, which cracked me up the other day when my class was telling me that. I had no idea boys got perms. And, but it kind of makes sense, I guess, because mullets are popular. And that's a trend that's come back. So mullets used to be popular, and now they're popular again. So it's kind of interesting. Clothing-wise, you all know, I mean, and really, I kind of have a feeling clothing trends are, and even hair trends, I think trends in style and clothing and hair used to be very, very rigid almost. I don't think they are as much anymore. I may be wrong, but it doesn't seem like they are. I think more people are more unique now and have their own style. I think that's kind of what happened. But again, when I was a little girl, bell-bottom pants were in. Big-bottom jeans. Back then we didn't have anything called bootleg or boot cut, but it was bell-bottoms in the 70s. And then for a while, recently, bell-bottoms came back. They didn't last long, though, really. They didn't last very long. They did for you, though. You like the bell-bottoms, huh? And so they did for a little while, but then they kind of went with boot cut. And so you know what I mean, though. You know what I'm talking about when we're talking about trends. You know exactly. Well, the beautiful thing is that the periodic table trends don't change. We have the exact same trends when I was a little girl up to now and forever. You know, all these trends are the same every time. So that's a good thing. These trends don't change. They always are the same. So we're going to look at 3 basic trends. Actually, 3 basic trends: ionization energy, atomic radius, and electronegativity. Those are the 3 trends we're going to look at. Now with you guys, I was really nice and pretty, and I gave you this pretty picture. In my 109 class, I don't give them a picture. Really, you don't need the picture because you're just looking at the trend. And what is the trend? So the first trend we're going to deal with is atomic radius. And Personally, I guess the reason they call it atomic radius is because radius is easier to say than diameter. But atomic radius really means atomic diameter. So if we were imagining these elements, these atoms, as being balls, if you can imagine it that way. Lucas, do you need your computer? Do you need it? Why don't you just put it down? That way it's not. Are you using your notes on it? Okay. Huh? Okay. They will be. They're already posted. Okay, I'll show you after class, okay? All right. So here's what we're looking at. So if we have an atom, if we have any atom and we think of it as this ball, then imagine ping pong balls, tennis balls, basketballs, exercise balls. You with me? Okay? So you're imagining, so that's what we're talking about when we think of the different radius, the different atomic diameter. That's what we're thinking of, is the different size. That's what we mean, okay? So there is a trend. Now you can see the trend because I gave you the picture. What's the trend? Down a family or down a group, what's the trend? Down. What's the trend? Bigger. Bigger. So the trend is atomic radius, and I'll put AR. Atomic radius increases from top to bottom in a group due to, now you tell me why. Atomic radius increases from top to bottom in a group due to. Why do you think the atomic radius increases? That's exactly right. Due to the addition of energy levels. That's exactly right. Guys, if you've paid any attention to my antics up here in the front of the room, what do I do? What do I do when we say we add energy levels? What do I do with my hands? Do I get bigger? Yeah, you've seen me do this day after day. First energy level, second, all the way to the seventh energy level. What's this indicating? A big what? A big atom. A big atom. Okay? So it's due to the addition of energy levels. Due to the addition of energy levels. Now, you would expect in the second energy level, which is where lithium and neon are, you would expect the atoms to be about the same size because they all have what? What do they have? They have what? The same energy levels. So, in other words, you would expect lithium and neon to be the same size. But the picture says differently. The picture says what happens across a period. They get smaller. So let's look at that trend and then let's talk about why. So atomic radius decreases from left to right across a period due to, so atomic radius decreases from left to right across a period due to who wants to tell me? Say it again. Not exactly. Because they wouldn't be losing at all. They'd be what? Gaining. No. Can you help me? You're exactly right. Can you bring me your chair? Bring your slide over in the chair. Ironically, he answered it, but he's going to help me demonstrate it. Okay? All right, you want to be positive or negative?
Positive.
All right. He is the positive in the atom, which means he's what? Protons. I'm going to be the electrons. Now let's just take lithium through neon. So if you, lithium has how many total protons? 3, which also means it has a total of how many electrons? 3, but how many are in the second energy level? Sodium, 1. Very good. So 1 electron is in the second energy level for sodium, right? And then as we go to magnesium, how many protons does magnesium have in its nucleus? 12. You with me? How many electrons are in the second energy level? How many electrons in the second energy level for magnesium? How many valence electrons does magnesium have? 2. Guys, you with me? All right, go on over to aluminum. Total of how many protons? 13. How many valence electrons does aluminum have? 3. 14 for silicon protons. How many valence electrons? 4. Keep going. 15, 16, 17, 18. By the time I'm in the wrong row. I went to third row. I talked about second row to start with, then I went to third. Sorry. Same principle applies. Bottom line, what's going on? Can I have your hand? Bottom line, what's going on? So we've got, bottom line, what happens when we are, let's just take sodium. 1 electron, how many protons? He's the positive, I'm the valence electrons. You with me? I'm 1 electron, he's how many protons? I'm sodium. We're sodium. Protons, 11. You with me? All right, keep going, magnesium. Magnesium, keep going. Who's larger? Sodium is larger. Who is larger? Lithium or barium? Lithium or barium? Who's larger? It's actually barium. Now, that is a harder one because one's farther right, one's farther down, one's farther left. I could ask that question because the energy level definitely overrides the biggest. I mean, that's a 6th energy level compared to a 2nd. Definitely much bigger, even though it's one place over to the right. Definitely. Now, would I ever ask you who's bigger, lithium or iodine? No, I won't ask you that. That's too complicated to tell. You can't tell. But I could say, who is larger, sulfur or rubidium? Who's larger, sulfur or rubidium? Rubidium. That should be easy. That diagonal should be easy to figure out. I won't ask you the opposite diagonal, okay? If you wanted a little diagram, make your diagram look like this. Atomic radius, small, big. If this is a diagram of the periodic table being a rectangle, you with me? Does that make sense? That's what it is. That's atomic radius. But again, you know, you don't even have to draw. I mean, you common sense knows energy levels are going to be bigger. More energy levels are going to be bigger. As you go right, they're going to get smaller because of that attraction's pulling those electrons closer. So what about atomic versus ionic? What about the cation compared to its atom? So what happens when we have the cation compared to its atom? Or the anion compared to its atom? Now, I'm not talking about random. I'm talking about, let's just take, for instance, calcium. Calcium cation, which is +2, compared to the calcium atom. Calcium ion compared to the calcium atom. Think about what happens and who would be bigger. Think about what happens to make the ion and who would be bigger. What do you think? +2 is who is what? Bigger or smaller?
Bigger.
Who disagrees? Good job. Why do you disagree? It's lost an entire energy level, hasn't it? It's lost electrons, but has it also lost an entire energy level? Tell me, how does calcium +2 become calcium +2? Now, I answer this question so you'll remember it. Look up at the periodic table, how does calcium +2 get made? How does it become +2?
Loses 2 electrons.
Where does it lose them from? Count down.
Yeah, would it be the, no, that's
Energy level. Ca. What energy level is it losing from? 4. Do you see that?
yeah,
See how it's in the 4th energy level?
yeah.
So it's going to lose 2 electrons out of the 4th energy level. Which 2 is it losing? It's losing these 2. Does that make sense?
Yeah.
So if it's losing these 2, what is its outer energy level now? 3. So is the 3rd energy level closer to the nucleus than the 4th energy level is? So is the Ca +2 smaller? Ca +2 has how many energy levels? 3. Ca has how many energy levels? 4. Does that make sense? That should go straight back to what we did last week on ion electron configuration notation. What is the ion electron configuration notation for calcium +2? Whose configuration notation is it? Argon. Do we agree with that? Argon has how many total energy levels? 3. How many energy levels does calcium have? 4. So calcium ion is smaller than calcium. So I'm going to make a note here. Cations are smaller than their atoms due to loss of valence electrons, thus energy level.
So will ions always lose an entire energy level?
If I'm asking you about ionic versus atomic radius, yes. I will not give you ones that don't. Like I would never give you iron 3 plus. Okay? I might give you iron 2 plus compared to iron, but I would never give you iron 3 plus. I'll make it so that it will. Okay? It'll always be an entire energy level lost on the ones I compare. Yes. Okay. The anion. The anion, so let's just take bromide compared to bromine. Bromide compared to bromine. Now, this one is a little trickier because we did this scenario when we went across the periodic table, and you saw how we got closer together as we went across and got smaller. That's for the atoms themselves. But the ion, who has more electrons compared to their protons now? Bromide or bromine? Bromide. Bromide has 1 extra electron. So can bromide's nucleus, which is positive, hold on as tightly to those? No. It's almost like tug of war. That's the way I think of it in my mind. It's like tug of war and who's winning. The negatives or the positives in bromide. The negatives are winning because they're greater. And so bromide actually is kind of like, oh, I can't hold on anymore. It's like when you eat too much and you just unbutton your pants. It's like, oh, I can't hold it in anymore. And that's kind of what bromide is like. And so bromide is bigger than bromine. Bromide is bigger, and so we're going to say anions are larger than their atoms due to the inability to hold tightly to the extra electrons. All right, so the second trend, ionization energy. Ionization energy, by definition, is the amount of energy required to remove an electron from an atom. It's the amount of energy required to remove an electron from an atom. Up until this point, I have pretty much made this out like a big fun game. Sodium wants to lose electrons so that it can look like neon. Magnesium wants to lose electrons so that it can be more stable and lose that outer energy level. Aluminum wants to lose 3. I mean, I've made it out like, oh, this is just fun and games, free, all this stuff. Nothing in life is free. Nothing is free. And in all honesty, it actually takes energy to remove these electrons. Now, the obviousness, hopefully you get this, size matters in the ionization energy, because think about it. If these atoms are big, big atoms, tell me about how tightly this electron out here is held. If I'm francium, and francium is this big, big atom out here, and it's got this one electron out here, is that electron going to be easily taken or harder to take than a smaller atom? It's going to be much easier to take. It's going to be much easier to take. Have I talked about my whole thing about how chemistry and people, it all goes together? When you all go to college, are you more easily taken to do stupid stuff? Yes? How many of you have done stupid stuff that you would never have done at home when you were close to the nucleus? Hopefully you're making good choices. But some of you are not making good choices, and when you got far away from the nucleus, because the nucleus couldn't hold on to you as tightly, when you were living under your own parents' roof, were you held on more tightly? Yeah, you're held on more tightly. But now when you go away, are you as tightly held? No. Are you more easily taken by all the Sims of the world? Yes, some of you are. Some of you need to straighten up and make better choices, because those choices will haunt you for the rest of your life. Okay? So be careful on those choices you make, for your sake. All right, now, I've just told you the trend. As you go down a family, what happens? Ionization energy what? Decreases. Why? Because the atom gets larger and the electrons are more easily taken. Are they as held tightly to the nucleus? No. So you already know. You already know. So I'm going to write it. So ionization energy, i.e., ionization energy from top to bottom decreases. Ionization energy from top to bottom decreases due to atom being larger and electrons less tightly held. From top to bottom, it decreases due to atom being larger and electrons less tightly held. Ionization energy. Look at the trend. What happens as you go left to right in a period? Gets increasing, takes more energy. Why? What happens to the size of the atom? They're getting smaller. Does that make sense? That it's going to match. It's going to have a relationship. It doesn't match it. It's actually the opposite trend. It's the opposite trend. But ionization energy from left to right increases due to atom getting smaller and electrons more tightly held. Which should perfectly match the thought process. Do these atoms on the right-hand side of the periodic table want to lose electrons anyway? Do the atoms on the right-hand side of the periodic table want to lose electrons. Do the atoms, listen to me carefully, I probably said it wrong the first time. Do non-metals that are over here on the right side of the periodic table, do they want to lose electrons? What do they want to do? Gain. They want to gain. So they're saying, if you're going to take one of my electrons, man, you are going to have to pay. Does that make sense? You're going to have to pay a very, very high price in energy because I'm holding on to it very tightly. Why am I holding on to it very tightly? Because I'm almost full. I would much rather do what? I would much rather gain electrons. I don't want to lose electrons. So if you want my electron, you're going to have to pay. It's going to cost you. Does that make sense? That's what's going on here. Now, if we look, though, at this table, there are breaks in the trend. There are 2 breaks. Now, this is where you separate what I say, the men from the boys and the women from the girls. If you can figure out why it has these breaks, then you understand what I've taught you for the last 2 weeks. What is going on at these breaks? Why? You would think this line just goes straight diagonal. But we have a break here, and we have a break here. Now, probably if you got on down, it would actually start evening out and not have the breaks. And that's because they all get bigger, which is what causes the difference. What is going on right here and right here? Think about what you know about electron configuration notation. Think about what I've told you about stability. When is an atom most stable? When it has a what subshell? Full or exactly half full? Now tell me why. Tell me why does boron, aluminum, and gallium have a lower ionization energy than beryllium, magnesium, and calcium? It's not energy level. What's it called? P. So boron, aluminum, and gallium only have, say it again, one in the P subshell, whereas beryllium, magnesium, and calcium all have a full S subshell. Do you see what's happening? So does it take less energy to remove the 1 out of P than it does 1 out of a full S? Yes. Yes. And so that's what's happening. That is what's happening. That is what's happening. And so what really is happening here then is, and guys, think about it. When we talked about, just think about aluminum. When we talked about making ions, when we looked at aluminum, we said aluminum has to lose 3 electrons to become aluminum plus 3, correct? Where is it going to lose the first electron from? P. Because it's unfilled. Yes? Then it will lose it out of the field. And then we said gallium. What are 2 logical charges for gallium? +1 and +3. Why is it +1? Because it loses that 1 out of P. Is that easy to remove? Yeah, it didn't take as much energy to remove that one. And then if it goes ahead and removes the 2 out of S, that would also. So I want you to make a note here. This would be the break in the trend. And this goes down due to removing 1 electron from an unfilled P subshell. This is higher due to 1 electron from filled S. Now, why do we have one more break? We have one more break. And I talked a little bit about this today when I talked about iron.
Half full.
Half full, that's exactly right. That's exactly what's going on here. Nitrogen, phosphorus, and arsenic are exactly half full P. Do you see that? Oxygen, sulfur, selenium are 1 electron over half full. So it's going to be lower energy to remove that one that's keeping it from being half full. Regardless, they still don't want to lose. But that's the reason for the trend break. That's the reason for the break in the trend. Okay? And that's good. Those of you that got that, good job. That you understand what we've been doing the last 2 weeks, and that's very good. Let me explain something real quick. Thursday, we have a lot to do Thursday to get finished with the test material. Please make sure you bring your notes. If you're not bringing notes, I do not. Let me show you what you're going to be writing. You don't have time to write all this, okay? Please print out notes for Thursday so that you can stay with me, okay? Print these out for Thursday. We have time to get it done, but you've got to bring your notes, okay? And I will see you on Thursday. If anybody needs these nomenclature notes, they're in the trash, so take them if you want them. The ones I went over today, you're more than welcome to have them. Just take the whole set. Just take all of it. That way you have all of it. And you can cover up my work and redo them again.
Exam with you tomorrow.
Oh, you're my, okay.
Yes. Yeah.
Ashton or Ash?
Ashley McGivern, yeah.
Okay,
Ash.
okay,
But,
okay.
I'll be there.
Okay, KTH, whatever she told you.
Huh?
KTH, whatever she told you.
Okay.
Whatever. I mean, I told her where it was. I don't remember.
I got it.
Okay. I have it in my email, but I don't remember off the top of my head.
Question on the homework.